this session, we'll discuss about the significance of standard hydrogen electrode, its arrangement, determination of standard electrode potential, electrochemical series, and how it can be used to predict the feasibility of a redox reaction, how to decide the anodic and cathodic electrode in an electrochemical cell, how to determine which metal on treatment with acid will liberate hydrogen. We have studied about electrode potential and standard electrode potential. Now let us understand what is standard hydrogen electrode, which is one of the most important aspects to determine the electrode potentials of other elements. It is also known as a reference electrode. It is basically an arrangement. There is a beaker which contains 1 molar H+ ion solution. A platinum electrode coated with platinum black is dipped into this solution, and a pure hydrogen gas at 1 atmosphere is bubbled. The whole arrangement is kept at 298 Kelvin. Therefore, the concentration is 1 molar, temperature is 298 Kelvin. The electrode potential of this hydrogen electrode is taken as 0. Now you might be wondering why platinum electrode is used for this experiment. That is because the platinum is relatively an inert metal. It does not undergo oxidation. Apart from that, the platinum has a capability to absorb hydrogen. So all these factors make the platinum the ideal metal to conduct this experiment. It is represented. See the representation. Platinum is solid, hydrogen gas and H+ ions is again in the aqueous solution. So there is a single slash which shows that there is phase change. So whenever there is a phase change, we put a single slash in the representation. By convention, the electrode potential of standard hydrogen electrode is taken as 0. So this is assigned a value 0. All other elements will have a value by coupling with standard hydrogen electrode. Electrode potential of other electrode is either greater or lesser than standard hydrogen electrode. Now how, we will see in the next slide. We have seen that electrode potential of other elements are either greater or lesser than standard hydrogen electrode. And the electrode potential of an electrode is determined by coupling it with the standard hydrogen electrode. The EMF of the resulting cell is given by E0 cell is equal to E0 cathode minus E0 anode. Why E0 cell? Because this is standard electrode potential. Here the temperature is fixed, that is at 25 degrees Celsius, and the concentration of the solution in all the measurement is 1 molar. Now you can see this arrangement. We have seen that the electrode potential cannot be determined in isolation. Now here we have taken the example of zinc. In this case, zinc acts as anode and the standard hydrogen electrode acts as cathode. Now you set up this and measure the voltage in the voltmeter. You get it as 0.76 volt. This is E0 cell. Now if you substitute this in our equation, here the electrode potential of standard hydrogen electrode is taken as 0. If you substitute in our equation E0 cell, you will get this. E0 cathode is SHE. By convention, we give it a 0 value. Since SHE is 0 volt, E0 Zn2 plus Zn is nothing but minus E0 cell, or the standard electrode potential of zinc is minus 0.76 volt. Let us understand one more case. See here. Here SHE is anode. The cathode is made up of copper. In the voltmeter you get a voltage of 0.34. Now we know the reaction. E cell is equal to E0 cathode minus E0 anode. Here SHE is anode. So E0 anode will be equal to 0. So E0 cell will be equal to E0 Cu2 plus Cu. That is equal to 0.34 volt. So you see, the zinc has a lesser value than hydrogen, whereas the copper has higher reduction electrode potential when compared to that of standard hydrogen electrode. I have already stated from the very beginning that among the two electrode potential, reduction electrode potential is taken for comparison. This is as per IUPAC regulation, so there is no confusion among the various laboratories.
We have seen the two examples of determination of the electrode potential by coupling with standard hydrogen electrode. Thus, all the elements will have their electrode potential, which is essentially the reduction electrode potential, either greater or lesser than standard hydrogen electrode. The arrangement of elements in the increasing order of their reduction electrode potential is called electrochemical series or activity series. In this series, the most active metal is placed at the top. The most active metal means those metals which have the highest negative value of the reduction electrode potential. Okay. Now, there is a very simple method to remember this electrochemical series. The exhaustive list of electrochemical series, you can have it from any textbook. Here, we will concentrate on certain metals. We'll arrange them in the increasing order of their reduction electrode potential, which is commonly used, which might be helpful for you from your examination point of view. It is actually a mnemonic. It goes like this: PSC Mas Intel H CMSGP. PSC Mas Intel HCMSGP. P stands for potassium, S for sodium, C for calcium, magnesium, aluminium, zinc, iron, nickel, tin, lead, hydrogen, copper, mercury, silver, gold, platinum. These are some of the few metals which we often use for the comparison. So the small list of element is quite enough from our examination point of view. Now let us understand some of the applications of electrochemical series. I am writing the electrochemical series in a horizontal manner. You can see also I have included in this list two more elements. One is lithium, another is fluorine. Lithium comes at the top and the fluorine is at the bottom. What are the significance of these elements we can see? All the elements that is on the left hand side of hydrogen has oxidation tendency. Further you move away from hydrogen, the oxidation tendency increases. And those elements which are on the right hand side of the hydrogen has a tendency to get reduced because the reduction potential is positive. More positive the reduction electrode potential, greater is the tendency to get reduced. So this picture is more than enough. It speaks quite a lot. Using this, we can understand a lot of things about the electrochemistry without much strain. Among this, we can say the fluorine has highest positive reduction electrode potential, and the lithium has most negative reduction electrode potential. What it means? It means that the fluorine is most easily reduced because it has highest positive reduction electrode potential. Hence, the fluorine, since it gets easily reduced, it acts as a very powerful oxidizing agent, because the substance which gets reduced is an oxidizing agent. Lithium, on the other hand, is very easily oxidized. Hence, it acts as a strong reducing agent. The second application is to identify the anode and cathode of an electrochemical cell. We know that the electrochemical series is arrangement of elements in the increasing order of their reduction electrode potential. It means that more negative the electrode potential, higher is the activity. Or rather, the electrochemical series is actually a reactivity series in which the elements are arranged in the decreasing order of their reactivity. Now, when we construct an electrochemical cell, the metal at the left hand side will act as anode with respect to the metal that is placed on the right hand side. For example, if we use magnesium and nickel in an electrochemical cell, the magnesium will act as anode with respect to nickel. But if we consider using nickel and copper, the nickel will act as anode, whereas the copper will act as cathode. So, it is very easy to identify the anode and cathode just by looking into the electrochemical series. Now let us understand the third application of electrochemical series. It is to predict the feasibility of a redox reaction. Remember that a redox reaction is feasible only in one direction. Well, what is the meaning of that statement? If you take copper and treat it with zinc sulfate solution, no product is formed. That is because the reaction is not feasible. Whereas, if zinc is treated with copper sulfate solution, zinc sulfate and copper is formed. That is, the reaction is feasible. What is the meaning of these two? It is essentially stating that you can store zinc sulfate solution in copper, whereas copper sulfate solution cannot be stored in a zinc container. I repeat, zinc sulfate can be stored in a copper container, whereas copper sulfate cannot be stored in a zinc container. As we have already discussed that electrochemical series is a reactivity series. Zinc is more reactive than copper because It is on the left hand side of the copper. Therefore, zinc can displace copper from its solution. It is essentially telling that more reactive an element can displace less reactive elements from their solution. Metal on the left hand side has a more tendency to get oxidized than the metal on the right hand side. Metal on the left hand side can displace a metal on the right hand side from their solution. All these statements are essentially the same. When a zinc rod is dipped in copper sulfate solution, that is something that you have studied in the +1 redox chemistry, the blue color of the copper sulfate fades and the copper starts depositing on the surface of the zinc rod. That is because zinc, being more reactive than copper, displaces copper from its solution. Whereas, if copper rod is placed in zinc sulfate solution, nothing happens. Now let us understand the fourth application of electrochemical series. It is essentially to predict those metals which can displace hydrogen from acids. From looking into the electrochemical series, we can say that all those elements which are on the left hand side of the hydrogen, or if it is written from top to bottom, the electrochemical series, all those elements which are above hydrogen in the electrochemical series are more reactive, or they have lower reduction electrode potential. Hence, these elements can easily displace hydrogen from acid.